Hi, and welcome back for another SPSS tutorial. This tutorial is going to cover simple linear regression in SPSS, and we'll actually do an example of multiple regression as well. So if we recall, the purpose of regression is to predict an outcome variable based on one or more predictor variables. Regression is just a more directed form of correlation. It uses the same properties as correlation in a somewhat more complex way. But at the end of the day, it's all about relationships between variables, which is what correlation does. So this is just an extension of what we can do with correlations. So in a regression, we want to predict some outcome variable based on one or more predictor variables. So we're going to use our record sales data set here. We've got 4 variables: album sales, advertising budget of a band, the amount of airplay that their song is getting, and perceived attractiveness of the band. So let's try to predict record sales here. So we want to develop a model, a regression model, that's going to predict the amount of albums that a band is going to sell, and we can use any of our other variables here as a way to make as accurate a prediction as possible about record sales. So let's start with a simple example. Let's try to predict record sales with advertising budget. So to run a simple linear regression, we're going to go to Analyze, to Regression, and then Linear. And in the menu we get here, we have all of our variables in our data set over on the left. And we have some options over on the right for where we can move these variables. So whatever we want to predict is going to be our dependent variable. So let's move the record sales variable over into the dependent box, since that's what we want to predict. Now the variables that we're going to use to predict record sales, we can move down into this box that says independent. So like we said, we want to use advertising budget. So let's move that into the independent box. The one other thing that I like to do when running a basic simple linear regression is click on the statistics box, click on the box that says descriptives, click continue, and click OK. So now we get several different boxes for our output. The first is just going to be descriptive statistics, so the means, the standard deviation, and the sample size for each of the variables, regardless of whether they're the the outcome variable or the predictor variable. We just have the general descriptive statistics for all variables. We have a table that gives us correlations between all of our variables in case we wanted that information. This variables entered and removed just tells us what variables are in the model. We can probably ignore that for now. The model summary variable gives us our effect size. So there's a couple pieces of information here. The one that's probably going to be the most useful for starting out with regressions is this R-squared value. So the R-squared value represents the proportion of the variability in the outcome variable, or the variable that you're predicting, that is explained by the model, right? So an R-squared value here of 0.335 indicates that about 33.5% of all the differences that exist in record sales were explained by our model, which uses advertising budget to predict record sales. So we've accounted for 33.5% of the differences in record sales based on the model that predicts record sales using advertising budget. Okay, so this is your overall effect size. This is what you want to report when you're writing up the results of this analysis. All right, the second table here is the Anova Table. This should look familiar if you've done analysis of variance before. We've got kind of the exact same layout of the table. The important statistic here is the F statistic and the significance value associated with it. What this F statistic, or this F test, is testing is the null hypothesis that the model is no better than the mean of the outcome variable in predicting the mean of the outcome variable. And what that means is, let's assume that no matter what the advertising budget for a band was, you just predicted the average number of album sales for every single band in our data set. All right, so that would be kind of the worst you could do at predicting how many albums somebody's some band is going to sell, is you just predict the average number of albums, right? And so what this F test is testing is the null hypothesis that your model is actually no better than that, no better than just predicting the average every single time. If we reject the null hypothesis, then that means that your model is better at predicting the number of album sales, predicting the album sales. It is better at predicting album sales than just predicting the average number of album sales every time. So when we get a significance value here less than 0.05, which we did in this case, that means that yes, our model is useful. It's predicting album sales based on the advertising budget much better, much more accurately than we would be predicting than based on just the mean of album sales, right? So this is what we want. We want to see a significant value here because that means we can reject that null hypothesis and we can say, yeah, our model is useful. It's better at predicting album sales than just the average, than just using the average of album sales, right? So we've got a significant test here. We can reject our null hypothesis. We say our model is useful. The last box here gives us the coefficients of the different variables or parameters in our model. So this is what we're going to use. We're going to use this for a couple of things. One, we can use this information to build the equation for the line that represents this model. So we do that with the unstandardized coefficients over here. So the first row where it says constant, the unstandardized coefficient, or the b value associated with the constant, that is our y-intercept. So this value represents, in our example here, it represents the amount of albums we would expect the band to sell if they didn't advertise at all. So the y-intercept is the value that you're going to be predicting. It's the value of your outcome variable that you would predict when your predictor variable is 0. Okay? So what we can say about this when we put it into real world terms is that we would expect the band to sell 134.14 albums if they didn't advertise at all. Okay? If the advertising budget was 0. All right, so that's what it means to be the y-intercept. The other value, the other row we have here, is the advertising budget row. This represents the what we would call the coefficient of the predictor. And so this tells us how much our album sales, our predicted album sales, change with each 1 unit of the predictor variable, with each 1 unit increase in the predictor variable. So this looks like a pretty small coefficient here, which would indicate a small change, but that's just because our album sales is represented in the thousands, right? So what this would indicate is when our advertising budget goes up by 1 unit, then our predicted record sales goes up by, it increases by 0.096 units, right? And that's a positive increase because we got a positive value here. If we had a negative value, it would be a decrease, right? But the 0.096 indicates that our predicted value of album sales is going to increase by 0.096 for each 1 unit increase in advertising budget. And so because our dependent variable, the album sales, is represented in the thousands, and because our advertising budget is also represented in the thousands, this really means that every time our advertising budget goes up by $1,000, we would expect our album sales to increase by 960 albums, right? We've just got to make that adjustment since all of these units are in the thousands. But aside from that adjustment, the important part here is that this is the coefficient that we would put in the equation for the line that we want to represent. So if we wanted to write an equation that represents our prediction of album sales based on advertising budget, that equation would be y, which represents our prediction of album sales. Y equals 134.14 plus 0.096x, and x represents our advertising budget, right? And so that describes how our predicted album sales are going to change based on the value of the advertising budget that the band is allocated. Okay? The other information here really just tells us whether these values are significantly different from 0. So you do get significance values here. And these are different from the overall model significance value. The model tells you whether your overall model is better than just using the mean of the outcome variable to predict the outcome variable. Each of these significance value in the coefficients box tells you whether the different coefficients are significantly different from 0. For our Y-intercept, that is maybe nice to know, but it's not. In most cases, it's not necessarily that important. So a significance value here for the constant or the Y-intercept just means that when album sales are 0, that the expected number of album sales, or I'm sorry, when the advertising budget is 0, the expected number of album sales are still going to be significantly different from 0. We would still expect to sell some albums even with no advertising budget. So that's all that this significance value means. The significance value associated with advertising budget itself is a little more important in the near term because it tells us that this predictor matters. It actually improves our prediction of album sales. If this value was not significantly different from 0, it would indicate that advertising budget doesn't really change our prediction of album sales. It doesn't increase it or decrease it. It adds really nothing to it, which is what would happen if this was not, if this value was not significant. So the fact that this significance value associated with advertising budget is less than 0.05, that means that this is a meaningful predictor, that it's actually useful to us in predicting album sales. So that's generally what we want. Now when we do a simple linear regression with just one predictor variable, if the model is significantly better at predicting the outcome than just the mean of the outcome, so if we get a significant test with the model, we will have to get a significant test with the only predictor in the model because that's the only thing that can be making that model useful. Now let's go through an example when we have more than one predictor. If we go back to our regression equation, go back to linear regression, and let's just add the number of the number of plays on radio 1, so the amount of airplay and the attractiveness of the band as predictors as well. And let's create an updated model with 3 predictors instead of just 1. So now what we'll see, our overall model is still significant, meaning it's still more valuable to us, it's useful in predicting our overall number of album sales. We'll also see now that all 3 of our predictor variables matter. They're all uniquely useful in predicting the outcome, and they all have different effects on the outcome. So we have unstandardized coefficients, so advertising budget increases our album sales by 0.085 or by 85 albums for each $1,000 we spend. The number of plays on radio 1 per week, so this is a much bigger coefficient, 3.367. That would indicate that every time the song gets played on the radio, we would expect to sell an additional 3,367 albums. And then finally, the attractiveness of the band. Every time the attractiveness of the band goes up, that rating goes up by 1 point, we would expect to sell 11,000 more albums, a little bit more than 11,000 more albums. All right, so this tells us how each of these variables affects the predicted number of record sales differently. Now, even though they have different amounts of effectiveness or there's a different prediction on how much they're going to change the overall advertising budget, that's a little bit different from how strong their relationship is with the outcome variable. And so that's what our beta column over here is, where it says standardized coefficients. Think of the standardized coefficients like a regression like a correlation coefficient. Your standardized beta coefficients actually are going to exist, that they can only have values between -1 and +1, just like a correlation coefficient. So these really, that's what these are used for. They're used so that we can compare the strength of the relationships that these different predictors have with the outcome variable, and we can say something about which variables have a stronger relationship than which other ones. So if we look at these beta coefficients, what we can conclude is advertising budget and the number of plays on Radio 1, or the amount of airplay, actually have much stronger relationships with album sales compared to the attractiveness of the band. With these beta coefficients of 0.51, 0.51, right, that's like a correlation coefficient of 0.51, which is a pretty strong relationship. The beta coefficient of 0.19 is still meaningful and it's still significant, but it's just not as strong as of a relationship. The reason why it has the biggest unstandardized coefficient, why it leads to the biggest increase in the attractiveness of the band, has a lot more to do with the units that these variables are measured on. So attractiveness of the band, if we look back in our data set, it only ranges between 1 and 10. So there's not as much variability here, so each 1 unit change actually is going to be a lot more meaningful in terms of its relationship to the number of album sales. On the other hand, airplay can go, looks like it has a low value of one play on the radio per week, and if we sort this value, it goes all the way up to 63. So we have a lot more variability. So each 1 unit increase is actually representing just a small portion of the overall variability in airplay. And the same thing with advertising budget. If we look at this, the biggest advertising budget is 2,271.86, and that's in the thousands. So this is actually well over $1 million in advertising budget, but the lowest value is down here around $9,000. So we're ranging between $9,000 and over $2 million. So each 1 unit here, or each $1,000, is actually a very small piece of all the variability in advertising. And so that's why whenever we look back at the output, each 1 unit increase maybe doesn't have as big of an impact on overall album sales, but there's so much more variability and there's so much more opportunity to increase by a lot more than 1, that these relationships are actually, in the end, between advertising budget and album sales and airplay and album sales, are much stronger relationships than the attractiveness of the band. Okay, so that's a lot of information about regression. Hopefully you picked up something from that. You can go back through and try to get little additional pieces as you go. Regression can be a little bit complex, but it can be also very, very useful. I find it one of the most useful tools in my research. So hopefully that helps you start understanding the basics of what regression is doing and what the values in your output mean. Come back again for the other tutorials I have up on SPSS, and enjoy.